Hello, this is Avdesh, and in this lecture, I'm going to share the views on Turing machine and its variations. So, before explaining what are the variation of Turing machine, let's first discuss what is Turing machine. So, Turing machine is described by these symbols collectively, where Q is the set of internal states, sigma is the input alphabet. So, these are the description. Delta is a transition function. Transition function, how it is different from finite automata or push-down automata is here the read-write tape, the head in finite automata or push-down automata. In that case, in finite automata or in push-down automata, this head is read-only head. For finite automata, there is no write facility, but for push-down automata, there is a write facility, but not in on this tape. There is a stack, and a push-down automata could write something on that stack. But in Turing machine, this the same tape in which the input is provided. The machine could write on the same tape, and the symbol what is written on this input tape is the element of this tau. This is the square bracket, or in some books it is also written as described as like this. This is the blank space. So if this is a machine and some input is given like 1101, so if this is the input on which this machine has to run, then the remaining part of these cells are blank. It is assumed that the remaining part of the cell is a blank symbol is written there. So it is like this. And this is a transition function that you are in a particular state, and what is written on the tape, on the basis of that you choose a new state, and you write down something on the input tape, and after that the read write head is either move left or right. So this is the description of Turing machine, and now we are coming to the description of some variations of the Turing machines. Now this is a particular type of machine, multi-tape Turing machine. In this machine, instead of one tape, there are multiple tapes. So here is the example where the two tapes are shown there, but it could be three or four, or many tape could be there. So this is one more, there is a variation on Turing machine, and the description of Turing machine is remains same as here, but the difference in this transition function. In simple Turing machine, the transition function is like this, but in case of multi-tape Turing machine, here is the difference. Now what is this? In multi-tape Turing machine, there are multiple heads, and each head is responsible to read and write to a particular tape. So whatever decision you are taking, that should be on the basis of the content of all the tapes. So here, if we would take n is equal to 2, that means 2 tape machine. For that, this could be a transition function. This is the example of a transition function for a two tape Turing machine. You are in a particular state, and at one tape, first tape, there is a symbol A. On second tape, there is a symbol E. Well, in that case, you would have to take some action, and that action is switch the state from Q0 to Q1, and write X on first tape, write Y on second tape, and after writing X and Y, the first tape move left side, and the second tape, the head of second tape would move on the right hand side. So here is the example. This is the scenario of this transition function. So you are in Q0 state. On first state, on first tape, there is symbol A. On second tape, there is symbol E. And once this transition function did its job, then what would happen? The state would change from Q0 to Q1. Now the state is Q1, and write X at the place of A. So the A is overwritten with X, and E is overwritten with Y. So these two cells are overwritten, and then first head is moved towards left side, and the second head is moved towards right side. So this is multi-tape Turing machine. But by doing this, it seems that the power of this machine would be higher, but it is not. The every action which is done in this machine could be simulated on your simple Turing machine. Like, so this is a two-tape Turing machine, and this is a simple Turing machine. And in this diagram, it is shown that the behavior of this machine could be simulated into this simple Turing machine. This is simple because uh, there is single head, one tape with multiple tracks. So there is no difference between power of these two machines, but yes, computationally, this machine would be more efficient than this one. But power wise, here, what does the mean of power of a particular machine? Power means the variety of the language a particular machine could accept is the power of that machine. So there is no difference between the power of these two machines. Means whatever this machine accepts, the variety of languages this machine could accept, the same set of languages could be accepted by this machine as well. So power wise, there is no difference, but yes, efficiency wise, this machine, multi-tape machine, is obviously more efficient than simple Turing machine or single tape Turing machine. Another variation of the Turing machine is, like, there are multiple, but I have written down the three variation of Turing machine. There's a multi-dimensional Turing machine. So here the tape is with multiple direction. It is not like similar to the multi-track Turing machine. It's a Turing machine with multiple dimensions. So the head could read this cell, either of the cell, and the current position of the head would be moved towards the next direction through these variation, left, right, up and down. This is designed for two-dimensional, four-dimensional Turing machine, but there could be many more direction as well. So this portion for transition function is same. You are in particular state, something written on the tape on particular cell, and as on the basis of this situation, you take an action so that you would go to some new state, write down something, some new symbol to the previous position, and then change the position of head, read right head, to this particular direction, either left or right or up or down. So if there are four dimensional, this would be the case, but it could be fifth, sixth, seventh, nth direction machine could be there. But at the same time, this machine also don't have more power than conventional single Turing machine. So this is multi-dimensional Turing machine. Next, Turing machine with stay option. I mean, it is just similar to the simple Turing machine transition function, but this S is additional. This S, what S says that after writing on that input tape, you don't move anywhere. I mean, you just tape is there. You are at particular position. Some symbol is there. So you are in particular state. Some symbol is written there. On the basis of that, you have to take some decision that you would go to some new state and write down some new symbol here, and then move either left or right or stay at same position. So after writing something on this cell, you don't move. If you don't have to move, you would choose this option S. So after writing this particular symbol, after rewrite this symbol, you won't move either left or right. You just stay at the same position. Then you could choose this option as well. But by doing so, again, there is no difference of power. The power is same of this Turing machine with single tape Turing machine with left and right option only. The next machine is non-deterministic Turing machines. Here, there is a you could say there is a so power wise there is no difference of single deterministic Turing machine and non-deterministic Turing machine. But again, the efficiency, the time complexity of this machine would be ideally lower than a deterministic Turing machine, because we believe that in Turing machine, non-deterministic Turing machine, this machine knows which one is the correct move. So it would move in only correct direction. But practically, if we are going to implement a non-deterministic Turing machine, this machine, the non-deterministic Turing machine, have to explore all the possible option. And if either of one option, if there is a way in which the input string would get accepted, then we would say that the machine would accept this particular string. So practically, it would take non-deterministic Turing machine take a lot of time, but theoretically, the machine would take the minimum time, lesser time than deterministic Turing machine. And this is the delta function or transition function of the non-deterministic Turing machine. The next machine would be like a universal Turing machine. This is not a variation, but this is an application of Turing machine in which we design a machine such that this machine, the universal Turing machine, take its input by another machine in encrypted form. Like the explanation of is like this, like something. We just encode any machine, a Turing machine. We encode a Turing machine. Then how could we encode a Turing machine? So let's say, how could we define a Turing machine? So Turing machine have some states, some transition functions, some symbols, and likewise. So if we encode each and every symbol, then what would happen if we encode states, if we encode the input symbols, then how could we encode the whole machine? We simply, like, for example, if we would write like for if we follow Unicode, then one is denoting something and double one is denoting something else, triple one is denoting something else, and so on. So this is unary encoding, and zero would be chosen as separator. So this what it is written is one, a zero separate for separation, and then double one. So this is a symbol, this is another symbol, this is another symbol. So likewise, we encode the character set. We could also encode the transition function. So this way we could encode the whole machine. So if we encode the whole machine, whole Turing machine like this, and then a word which would run in this machine. Suppose if a machine is denoted by M, and we simply encode that machine into this fashion. And what our question is, whether this word W would be accepted on this machine M or not. So for that, we would create a new machine, universal machine. For a universal machine, what would be the input of this machine? A description of M, that means this encoding of the machine, and then W. So now the question is whether this W would be accepted on this machine M or not. And this is for internal purpose use, whether to find out at after processing some symbol wherever this machine would halt, or would be on, suppose suppose this machine, this M is initially on Q0. So here would be some Q0 state initially, and then this machine, universal Turing machine, read a character from here, and now this machine, the M machine, if M machine would be at Q0 state, and if it were input 1, then which transition function would be chosen? So this MU machine would choose that particular transition function and move accordingly. So this MU machine simulate the M machine on the word W. I'm repeating, the MU machine, universal Turing machine, would simulate the M machine on the word W. So when M accepts W, that means MU accepts this Turing machine with W. So for this machine, for MU machine, the input would be M, W. So M is an encoding and W is a word for which we are interested, whether this W would be accepted by M or not. So this is our question, and MU would reply yes or no. If M accepts W, then MU would say yes. If M rejects W, then MU would say no. So this is a universal Turing machine. And